Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to show you a way of constructing arbitrary vector bundles, and it uses something known as transition functions. These are very, very important tools to use in the theory of vector bundles, and this construction actually mimics the way we construct the Mobius band. These transition functions also allow us to compute with vector bundles in many ways, and that's why it's an important tool. Okay, so let's remind ourselves, how do we construct the Mobius band? And the usual way you do it is by cutting and pasting. Okay, so we'll look at it in the following way. So what we'll start off with is a little strip like this, okay? And so we can think of this as a trivial line bundle on this interval given by this black line here. And above each point of the black line, we have a copy of a real line, which is given by these red vertical lines here. And what we can do is we can glue another copy of that to this strip here. So we have another strip here, which we glue to this one here. And we can do it in several ways. Okay, so the first way gives us the trivial line bundle, which is the cylinder. Okay, so what we can do is we can just glue this part of this strip to this here, and the other part round the other way, so that you get basically just a cylinder like that. But to get the Mobius band, what you need to do is you need to twist this and then glue it together. Okay, so it's as follows. We just take this bit here, we glue it the same way, but the other end of this strip, we glue it in the other way. So we glue it like this. And that's how you get your Mobius band. Okay, so what does gluing really mean? Okay, so that's the thing that we need to have a look at. Okay, and that involves talking about gluing data. So what you have is you want to basically identify certain points on one strip with points on another strip. Okay, so what you want is you basically want to give a function from a part of this strip to this strip, which tells you, well, any point here, how do I glue it to a point on here? Okay, so let's see that process. Okay, so let's look at the part that you want to glue to. So for example, you want to glue on this end here. So this part here, you can look at, it's going to be some sort of a trivial bundle, so it has to form some open subset of this black line here, so we'll call it U cross, and you have some trivial bundle here. So here it will just be the field, but in general it'll be something of the form the field to the R. And what you need to do is you need to glue the corresponding version of that U on the other strip cross FR to this bit here. So what does that actually mean? That means that you'll have two copies of U cross FR, one on one strip, one on another strip, and you need to have some sort of vector bundle isomorphism between these two. And that's the gluing data that's required for you to glue one strip to another, in this case, and more generally construct vector bundles. Okay, so let's see what this gluing data really amounts to. Okay, so remember what you want to do. Okay, this is a vector bundle isomorphism. So each of these red lines has to be identified with a red line over here. Okay, so each of the fibers here, which corresponds to a vector space in your family of vector spaces, gets identified with one of the vector spaces over here. Okay, so let's look at that. Let's fix some little u inside this u, some little u inside here, and look at the fiber above this little u here. So that's going to be the vector space FR, and similarly on your other strip, okay, it'll be some vector space which is also just given canonically by F to the R. And you want to identify these two, and this has to be a vector bundle isomorphism, so this should be an isomorphism of vector spaces. So essentially, this is just given by some invertible linear matrix, which is R by R. So basically, if we denote this invertible linear matrix by 5U. 5U is just inside GLR of F. So that tells you what happens on the fiber above U, and as you vary U, you get this whole vector bundle isomorphism. Okay, so this vector bundle isomorphism, of course, has to be a U morphism. So that actually tells you what form this bundle isomorphism must take. Okay, so let's suppose we have UV is element inside this trivial vector bundle. Where does it get sent to? To be a U morphism, of course, the U coordinate has to stay the same. So this goes to U comma something. And what does it do on the fiber? What does it do to this V? Well, basically you apply this linear map here. So that's phi of U. So this V gets hit by phi of U. And that's the form of this bundle isomorphism. So this phi of U, this is a function of U. So it's a map from U to the set of invertible R by I linear matrices with entries inside F. And this is the gluing data that allows you to glue this part of the strip to another part of the strip. And it gives you vector bundle isomorphisms when you have trivial vector bundles like this. Okay, so now we have the notion of a gluing data. Let's see what happens if you're given some sort of a vector bundle and look at the notion of transition functions. Okay, so suppose here now we have a vector bundle. So remember that's a map from V to X. So this is a vector bundle on X. V is the vector bundle, and suppose it's rank R. Okay, so each of the fibers, each of the P inverses of points inside here, they're vector spaces of dimension R over your chosen base field. And suppose we have an open cover of this X, and the open cover is given by these U alphas, where the alpha ranges over some index set A. And we're going to assume that on this open cover, that this vector bundle trivializes. Okay, so what does it mean, trivializes? So remember, to be a trivial vector bundle means that it's a product of the base space with F to some power, okay, the rank of the vector bundle. So in this case here, for this open cover to trivialize X, it just means that for each of these U alphas, if you restrict this vector bundle to that U alpha and look at P inverse of U alpha, that's isomorphic to the trivial vector bundle U alpha cross F to the R. And let's assume that we actually pick an isomorphism. So this is a bundle isomorphism over U alpha, and we'll pick an isomorphism theta alpha. Okay. So above these U alphas, it's quite easy to study this vector bundle. It's just trivial like this. Okay. And as long as you have this actual isomorphism, you can study this vector bundle just by looking at the trivial vector bundle quite easily. Of course, if you have two different open sets inside this open cover, you have a trivialization on each of them. So on each of these open sets, U alpha and U beta, for example, you'll have an isomorphism of this form. So you get a theta alpha on here and a theta beta on the U beta. And so you can study what happens on the intersection in one of two ways. You can use either this isomorphism, theta alpha, for this U alpha, or theta beta. And of course, the transition function, which is very important here, is, well, how do you pass from one of these trivializations to the other one? Okay, so let's look at that. So what is the transition function here? This is something about what's happening on the intersection, where you can use either of these trivializations. So we'll denote this intersection by U subscript alpha beta. So U alpha beta goes from, which is defined to be U alpha intersect U beta. This is going to be a map from this intersection to invertible R by R matrices with entries inside F. And what type of information does this give? So if you remember from here, this allows us to give bundle isomorphisms from that open set U alpha beta, and having the trivial bundle on that, it gives you an isomorphism of that trivial vector bundle to itself. Okay, so where do we get such a thing? Okay, so let's have a look at the vector bundle restricted to this intersection here. Okay, so that's P inverse of U alpha beta. Of course, we can restrict this isomorphism just to the intersection and see what happens. So if we restrict theta alpha to just this intersection u alpha beta cross f to the r to the corresponding part of the vector bundle, that's P inverse of u alpha beta, you have an isomorphism like that, theta alpha restricted to this domain here. So that's using the first trivialization theta alpha. You can also use the second trivialization theta beta to go back. So there's a map from theta beta from u beta cross fr to P inverse u beta. So you can invert this map above the intersection, and if you invert it, what you get is a map from P inverse of u alpha beta to, well, the corresponding part of this trivial vector bundle u alpha beta cross f to the r. So at the end of the day, what you see is, given this vector bundle, and if you're given two open sets in this open cover, you get a bundle isomorphism from u alpha beta cross f to the r to u alpha beta cross f to the r. And since you get that, of course, this must come from a map phi alpha beta from this intersection u alpha beta to GLRF. And basically, that tells you how to go from one trivialization to the other. So each point of here tells you how to write it. This trivialization tells you how to write it in this coordinates, this trivial vector bundle, using theta alpha, and using the other one, you use this one. So basically, if you want to glue this trivial vector bundle to this trivial vector bundle, to recover the original vector bundle V here, this is the data that you need. This is the gluing data that you need, just as we constructed this Mobius band by gluing two strips together. Now, these transition functions actually capture all the information about the vector bundle. And to see that, what we're going to do is we're going to reconstruct the vector bundle just using these transition functions, which we're going to think of as gluing data, just as we built that Mobius band using a gluing type of construction. Okay, so let's just remind ourselves, in that gluing construction, we pasted a strip to get the Mobius band, and also the trivial line bundle, the cylinder, which is a line bundle on the circle. And these transition functions are the things which give us this gluing data. Okay, so we're going to consider the analog of these two strips. Okay, and in other words, what we'll do is we'll look at all these trivial vector bundles. Okay, so we assume we're given all these phi alpha beta, these transition functions, these alpha and beta range over the index set for the cover, this open cover, which trivializes this vector bundle. And we look at this disjoint union of all these trivial vector bundles, u alpha cross f to the r. And what we do is that we just have to glue these together. And gluing them together just means that we put an equivalence relation on them. And what's that equivalence relation? Okay, so sometimes we'll need to glue some part of u alpha cross f r to some part of u beta cross f r. Okay, and when does that happen? So suppose you have a u which is both in u alpha and inside u beta. Okay, so you can consider one of the points inside here, for example, u comma v. So v will be inside fr, u will be inside u alpha and also inside u beta. Now you can think of this u inside u alpha or inside u beta. And so this will correspond, so this element of this set here has to be glued to an element inside u beta cross f to the r. And which element is that? Okay, it's just u comma the corresponding element of f to the r, which is given by this gluing data here. So we just apply phi alpha beta to this u, and this r by I matrix you hit with v, and that gives you the new element of f to the r. That's the corresponding element. Okay, so this is the way you glue the vector space above u inside u alpha cross f to the r to the vector space above u inside u beta cross f to the r. That's the gluing data that's involved. And once you perform this, it turns out that you do actually recover the original vector bundle V. So really this transition function does capture all the information about this vector bundle, at least up to isomorphism. Now this is a fairly general procedure, and what was required to actually perform it, okay? All you need are these functions phi, alpha, beta. So let's have a look at the converse question, okay? Suppose we don't start with a vector bundle, but we just have all this gluing data, okay? So these are just functions phi, alpha, beta inside our geometric category, which go from this intersection u, alpha, beta to this GLRF. And we can just write down this quotient inside our category. And it turns out that this will define a rank R vector bundle as long as it satisfies the following what's called a co-cycle condition. So they can't be completely arbitrary, they have to satisfy some conditions. So the first one is that for any alpha, phi alpha alpha equals 1, just the identity matrix. So that means that when you want to glue u alpha cross fr to itself, of course, you don't want to glue one point to a different one, okay? This is actually part of the vector bundle. You don't want to identify two different points of the vector bundle. So that's a natural thing to have. The other thing is what happens when you look at not just the intersection of two open sets in the cover, but three. Okay, so here you have u alpha, u beta, and this transition function phi alpha beta tells you how to glue the trivialization here to the trivialization over to u beta. But what happens if you want to glue both of them to a third open set? Say u gamma. So here we'll have u gamma in this third open set. Well, you can glue the trivialization above u alpha directly to u gamma, but that should be the same as if you glued the trivialization above u alpha to u beta first, and then u beta to u gamma. So this is something that you can do on the triple intersection. So what you want to make sure is in the triple intersection, those two things are the same. So in other words, what you want is that if you glue directly from the trivialization above u alpha to the trivialization above u gamma via phi alpha gamma, that's the same as if you did alpha to beta, u alpha to u beta first using phi alpha beta, and then applied phi beta gamma to go from u beta to u gamma. So these two equations are what's called the co-cycle condition. And as long as these are satisfied, you can actually build this rank R vector bundle. And of course, this rank R vector bundle will trivialize on that open cover u alpha. Okay, so there's just a couple of things to note about this. So this is wonderful. It really completely generalizes that construction of the Mobius band that we saw before, just by, in that case, it was gluing together two strips, so two trivial line bundles. And this is completely general. Now, this notion of transition functions, these transition functions you associate to a vector bundle are not unique. Okay, so let's see why that's true. So firstly, these trivializations, these isomorphisms, theta alpha, they're not uniquely determined. Indeed, what you can do is you can have some isomorphism of the trivial vector bundle u alpha cross fr, and it's quite easy to see what they are, and we've gone through that. They're basically just given by maps from u alpha to GLRF. And so you can change this isomorphism by some bundle isomorphism here, and you'll get a different set of theta alpha. And then when you look at the transition functions here, how you define them, of course, if you change this theta alpha or this theta beta, probably this function will change as well. Okay, so these transition functions are not unique. The other thing which is a bit more interesting is that, well, you have to pick an open cover for this x to get this to get these transition functions. And of course, you can actually change this open cover as well. So for example, if the vector bundle is trivial on u alpha, then it's also trivial on any open set inside it. So you can replace u alpha, for example, with an open cover, and that'll be trivial over there. And then you can look at new transition functions, because this trivialization, theta alpha, will also induce isomorphisms, so trivializations, for each of the open sets inside u alpha as well. And if you use those, you'll get a different set of transition functions. And of course, in fact, the index set will be quite different here as well. But what's rather nice is that, to a certain extent, these are, so to speak, the only things you can do. So in other words, you can actually determine when two vector bundles are isomorphic just by looking at the transition functions. If the transition functions can be gotten from each other just by one of these two methods, so either by changing these trivializations here, or by refining the open cover by replacing each of these U alphas by an open cover of them, then those vector bundles will be isomorphic. Okay, so let's have a look at some examples of constructing vector bundles using transition functions. And the example I want to have a look at is very important in algebraic geometry. That's the construction of holomorphic line bundles on the complex projective line. Okay, so let's just remind ourselves what's the complex projective line. The complex projective line, also the Riemann sphere, you can think of as just, firstly, the set of complex numbers where we've added the point at infinity to make a one-point compactification. To get the structure of this has the structure of a complex manifold. Of course, one patch, you just have the C itself. You can look in a neighborhood of 0, and there you have one patch. You can also look in a neighborhood of infinity. So that gives you the other patch, and that we're going to denote by the affine line A1. So it's just a copy of the set of complex numbers, and the complex number here is denoted by Z inverse. Okay, so it's a union of A1 with coordinate Z with the affine line with coordinate Z inverse. And so we've written this projective line as a union of two open sets, and I'll denote the open sets by U0, a neighborhood of 0, and U infinity. With this open cover, we can try to glue trivial vector bundles to get non-trivial vector bundles. So we need to look at the intersection of these two as well. So what's the intersection? Of course, that's in my old notation was U0 infinity, and that's just U0, and you have to remove the point which is missing here, which is the 0. So it's C minus 0. Okay, so we need to glue trivial bundles on here and here. And the way I'll do that is given by a transition function from this patch to this patch. So for every natural number n, I'm going to define a line bundle On using the following transition function. This phi 0 infinity goes from this intersection U0 infinity to, we want something that's rank 1, so it'll be GL1C, so we're working in the complex setting. And what are the invertible 1 by 1 matrices? Of course, they're just the non-zero complex numbers, so C cross. And this function is easy enough. It's just Z maps to Z to the minus n. So note that this is a non-zero complex number always, because your input Z is inside here, C minus 0. So you're looking at non-zero complex numbers only. Now the way we set things up, of course, to define a line bundle, we need to actually give more transition functions. Okay, we also need to say, how do we glue U0 to U0, so phi 0, 0. And of course, the co-cycle condition says that, well, you need the identity matrix C, so that's just 1. Also, how do you glue the trivialization above U infinity to U infinity? That again is just the identity matrix here, 1. And then how do you glue U infinity back to U0? Well, of course, it should be, so to speak, the inverse of this, okay? So the co-cycle condition tells you that that's the case, and that means that you just want to make sure that when you multiply this with whatever this transition function is here, you'll get the identities here. So of course, that's the function phi infinity 0 of Z is equal to Z to the n. So when you multiply this with this, you get 1. Okay, so now we have the data which defines an actual line bundle, a holomorphic line bundle on the complex projective line. Well, what do they look like? Well, the best way to answer that question is to have a look at the sections of these line bundles. So we'll do that next. And in the process, we'll see that these transition functions actually allow us to really get a good understanding of these sections and really compute these vector bundles. Okay, so let's suppose our section S So this goes from P1 to our line bundle ON. And let's see what happens. Okay, so the way this was defined was using transition functions and hence gluing trivial bundles. So we'll look over those trivializations so on each of these patches and see what we get. Okay, so that's done over here. So we'll look on the first patch, A1Z, this affine line. Okay, so on this affine line, you can treat the vector bundle as just A1Z cross C. And of course, in the previous video, I showed you what the sections of this look like. Essentially, they're just functions A1Z to C. Okay, so how does that work? So that's given by a map from A1Z to that product. So it's in Z to something of the form Z comma f of Z. And this f of Z has to be a function from A1Z to C. So of course the sections we want to have a look at here are holomorphic, since we're working in the category of complex manifolds. So you want this function f of Z to be a holomorphic function on this A1Z, which of course is just the open set of complex numbers here. So since it's holomorphic on the whole complex plane, you can write it in terms of a power series, f of Z equals A0 plus A1Z plus A2Z squared, and so forth. Okay, so that gives us a description of a section, at least on this open patch. Of course, we don't know whether this gives you a section as yet, because we have to consider the other patch as well. So we've defined the section at every point except for at infinity. That's the point missing from here, from this open set here. So can you extend it to a function which, so that it's defined at infinity as well? So let's look on the other patch and see whether you can. Okay, so on the other patch, that's given by A1Z inverse. Okay, so you're going to restrict the section now to this patch here, and let's see what it is. Well, most of the time this has already been defined, because it's defined up here using this f of Z. So at every point except for at infinity, it's already defined, and let's see what it has to be. Okay, so Z maps to this thing here in this chart, but now we swap from this chart to this chart over here. And remember, the transition function is the thing which tells you how to swap from one chart to the other. Okay, so what's the swap? Well, in ON, it's given by this 1 by 1 invertible matrix, so you just multiply it by the Z to the minus n. So here you go, this section on this chart in the neighborhood of infinity maps Z to, well, Z comma, and the corresponding thing here is not f of Z, but you have to apply that gluing data, the Z to the minus n. So it's just Z to the minus n times f of Z. And so, well, is this well defined? Can you make this defined at infinity, or when Z inverse equals 0? Okay, so let's have a look at this function, Z to the minus n f of Z. And what we need to be able to extend it to infinity is to make sure that this function is actually holomorphic on that patch, A1Z inverse. Okay, so let's have a look and see whether that's the case. And it's easy to do if you use the power series expansion for f of Z. So here's f of Z, and we just multiply it by Z to the minus n. When we do that, you get A0 rather, times Z to the minus n, plus, and you keep going until you get to the nth term, an, and then you add the rest of the terms, an plus 1 to the times Z plus, and so forth. And remember, this has to be holomorphic on this patch A1Z inverse. So what it has to be is it has to be a power series in Z inverse. So you can't have any Z or Z squared or higher order terms inside Z. So that means that all of these coefficients must vanish. And as long as they vanish, this will define a holomorphic section of this line bundle. Okay, so what do we see? So basically we see that this will define a holomorphic section of the line bundle if and only if all the terms beyond from the an plus 1 term onward are 0. So in other words, this is just a polynomial of degree at most n. So this is a rather interesting fact. that the holomorphic sections can be described in this way as simply just the polynomials of degree less than or equal to n. And that actually tells you some interesting things about all these line bundles, okay? Because it may be that when you define using transition functions, you get a vector bundle which is trivial. It's not so easy to tell whether that's the case. But here, what do we see? For example, we might ask the question, are all these line bundles isomorphic to each other? And we see straight away that that's not the case. Because for there to be non-zero holomorphic sections, of course, you need this n to be non-negative. So On has non-zero sections if and only if n is a natural number. And in fact, we see as a result of this that O of any non-negative number is not isomorphic to O of any positive number. So these transition functions have allowed us to actually compute the sections, in this case, the holomorphic sections, and actually show us that in the process, this construction has given us some non-trivial line bundles. Okay, let's study these holomorphic line bundles on P1 further. And the way we'll do that is by looking at zeros of sections of vector bundles. So recall that sections of vector bundles are really generalizations of the notions of functions. And why do we look at functions? Well, there really are very many reasons, but two of the important ones are firstly, to give maps. And we saw that sections of vector bundles can be used to give maps into projective space. And the second thing is that you can look at the zeros of a function, and looking at the zeros of a function often gives you interesting subsets. And it turns out that you can also look at zeros of sections as well. So that nicely generalizes these notions from functions. Okay, so suppose you are given some vector bundle V and you have some section S from X to V. What is its set of zeros? Okay, so its set of zeros I'll denote by Z of S, and it's going to be a set of points inside my base space X. Okay, and we'll just use the same definition as before. Remember, S is a function from X to V, and we just require looking at all the X such that S of X equals 0. Okay, so what does this equals 0 mean? So remember, where is this S of X? Okay, this S of X is inside the fiber of V above this little x. And this is a vector space. So being a vector space, it has a distinguished element, the 0, and you can ask whether this S of X equals the 0 inside this Vx. So here the notation 0 means something different depending on x. Okay, it's the 0 inside the vector space Vx. But nevertheless, this definition makes perfect sense. You can ask, when does this section take on the value 0? So unlike a function, you can't say when does this value take on when does this value S of X take on a value like 1 or 2, but 0, that's okay because that's a distinguished element of this vector space. Okay, so let's return to our example of these line bundles On that we saw before, and let's have a look at zeros of sections. So we'll pick a section S which is non-zero and see what happens. So remember how we got these sections. We looked on each of the open patches. So we can look on this open patch here, the affine line with coordinate z, the neighborhood of 0, where we throw away infinity. And there it's just given by some holomorphic function f of z, which to be holomorphic also at infinity, we require the degree of this, firstly that this is a polynomial, and also that the degree of this polynomial is at most n. So we can write it like this, a0 plus up to a dz to the d. Okay, so it's good to also see what it looks like on the other patch, a1z inverse in a neighborhood of infinity. And so remember, you just multiply this by z to the minus n, and that's what you have here. And now let's have a look at the zeros of this section. Okay, so on this patch here, it's quite easy to see what happens. This is just the trivial vector bundle. So the trivial vector bundle is just a1z cross c. And so S is just given by mapping z to, or z here, and f of z over here. So f of z is inside this coordinate here. And This C is basically your Vx, so you want it to be 0 there, so you just look at the zeros of this polynomial. And with multiplicity, of course, we know there are d of them. So S has d zeros with multiplicity on this A1Z. And they just correspond to the zeros of this degree d polynomial. What about on the other patch? So the only point that we're missing here is what happens at infinity. Okay, so here we want to look at this at infinity, which means as a polynomial in Z inverse. And what is the order of the 0 at Z inverse? Well, you have this term here is that what tells you what's going on, Z to the d minus n. That tells you that the order of the 0 at infinity is n minus d. So as d zeros on the complex plane, or the affine line, complex affine line, and at infinity it has n minus d zeros. So this is rather interesting, because what does it say? Any non-zero section of ON always has n zeros, okay? At least if you count multiplicity. And furthermore, most of them, so most of these, I guess, if you range over all the sections, holomorphic sections of ON, most of them will have degree n, and most of them, the roots would be distinct. So we'll actually have n distinct zeros. So the set will be a set of n points inside here. And that tells you a lot about these line bundles. That tells you extra information that we didn't see before. In particular, suppose you have two natural numbers, so you do have non-zero sections of these line bundles, so m and n, and suppose they're isomorphic. Well, you can take a section of one of them, which will correspond to a section of the other one as well, and look at the zeros of them. On one side here, you'll find that there are m zeros, and on the other side, you'll find there are n zeros. So of course, the m and the n have to be the same. M equals n. And in particular, if m and n are distinct, you'll get non-isomorphic line bundles. So that means that in our construction, we actually get lots and lots of different line bundles, an infinite number. And in fact, this holds true even for negative numbers here. So given any two integers, m and n, you have an isomorphism like this if and only if the two integers are the same. So to sum up what we've done in this video, we looked at a wonderful way of constructing vector bundles using transition functions, which is completely analogous to how we constructed the Mobius band by gluing strips together. So the transition functions give you this gluing data. And what's more, we saw that actually using these transition functions, you can really compute a lot of things. So for example, we computed all these sections of all these line bundles on P1. I hope you enjoyed this adventure in pure mathematics.